Our Unit 4 test. A couple of you are still finishing up. So we're going to dive into Unit 5 today. I remember we said this was that other unit that was here to prepare you for what you would need to do if you were to go on to a bachelor's degree after doing either an associate degree nursing program or paramedics program or health information technologies, any other program that takes math with health professionals, dosage type calculations. And one of those courses you would have to take would be statistics. And so, Unit 5, we're going to talk about statistics and do some calculations with it. But it's important today that we lay out some background information because statistics is almost like learning another language. So the first real point is, why study statistics? And there are a lot of fancy answers I could come up with for this, but it really boils down to two things. One, to be an informed consumer. Like it or not, statistics are all around us. Political advertisements are showing, 54% approval rating for this politician or whatever. Any advertising, any sales campaign is using statistics. 3 out of 5 medical professionals support this or whatever. And so understanding what those mean. When they say that 3 out of 5 doctors recommend this medication, they're not saying that 3 out of 5 doctors say this is the best medication. It just means 3 out of 5 doctors agree that this would meet the minimum necessity for treating this. But there might be a dozen other medications that they also all agree would meet those requirements. Second is to make informed decisions or make data-based decisions. And this is a little bit more of an advanced topic that we won't have a lot of time to get to in this course. Gets into confidence intervals, hypothesis testing, linear regression analysis. You may have seen that in an algebra class at some point, or a data analysis unit of another course. More of the advanced topics that you would see in the last half of a semester of a full-blown statistics course. When you get into, you might think, well, data-based decisions, that's not hard to do. But it's really more complex to break down data and take that information to make a decision than you might think. If you look at most large corporations, your CEOs and your CFOs, the people that run those corporations, they have two things in common. One of the common things is a background in accounting. You need to understand how the money works. And the second is an understanding or a background in statistics. Being able to look at data and information, know how to break it down, and know how to interpret it so that you're making correct decisions based on that data. So let's define some of the vocabulary that goes with statistics here. And the big term, most important term, is something called a population. In statistics, a population is the group that we want to learn about. It could be a group of people, could be a medication, is any group. It could be parts coming off an assembly line. That could be our population that we're looking at. Any group of any type of things that we want to learn about. As we look at that population, there's something called a parameter. And a parameter is a piece of information describing that population. Now, in many cases, there's a lot of parameters out there describing a population. But we are looking at one thing that we want to learn about that population. So there's something more specific called a parameter of interest. let's do an example here. Our example is, let's say we want to know, we want to predict the winner of the next mayoral election. Well, first we need to define the population there. You might want to say, well, the population is the candidates. Well, that's not true. Yes, we want to know which candidate is going to win, but that's not the group that decides that. Our population here is really the voters. Now, it might be tempting to say all registered voters, but not really. Because especially in a mayoral election, you're lucky if 30% of the registered voters show up. So our population here is really voters that will vote. The ones who don't plan on voting, we don't care about what they think because they're not going to make this decision. They're not going to determine who wins. Now, there are a lot of parameters of this population. They're all over 18 because you can't vote if you're under 18. They're all legal residents of the city or municipality. They meet all the qualifications to vote and all that. But we don't care about any of those. We care about the parameter of interest. And that parameter of interest is what percent plan to vote for each candidate. We don't care about all those other things that describe this population because, again, they're just defining the population. We want to describe this item that we want to learn about. We want to learn who's going to win. Now, if we wanted to collect information from the whole city, all of those voters who are going to vote, that process would be called a census. We did a census in 2020. We do it in the United States, we do it every 10 years, where we try to gather information from every living person in the United States. We've never successfully completed a full census because there's always at least one person who doesn't get their information gathered, but there's an attempt. Now, oftentimes, doing a census on a full population is not practical. And we spend billions of dollars every 10 years in the United States to do that 10-year census. And we're still not successful getting everybody. So it's very expensive, very time-intensive, and labor-intensive. We'll start in January, and we won't finish up until September or October before we finally decide we've gathered all the information we're going to be able to gather. So in most cases, instead of looking at a population, we look at something called a sample. And a sample is just a subgroup selected from the population. And it is this group that we actually gather information from. We'll talk about why we use a sample here in just a little bit. But now, if we're describing a sample, the word statistic, the name of this unit, a statistic is a piece of information or just information describing a sample. So a parameter describes a population, a statistic describes a sample. So the information, since we're gathering the information from a sample, most information that we gather will be statistics. And of course, just like we have a population of interest, or a parameter of interest, we have a statistic of interest. So back to our voter example again. Even in our sample, all of them will be over 18. They should all be legal residents. They're all legal voters in the area. We don't care about those statistics. Those are things that describe the sample, but we don't care about those. What we care about is what percentage of the people in our sample plan to vote for each candidate again. And of course, a survey is similar to a census, only it's gathering information about the sample. Now, in some cases, when we're dealing with people, it's generally a survey. But if we're looking at drug testing or parts coming off an assembly line, that survey can take the form of an experiment as well. So before we get into anything else, the big question comes up, why use a sample? Why not go ahead and gather information from the whole population? You would think that would be pretty reliable if you can get the information from the whole population. Be a lot better than just taking a sample and hoping it's the same. Well, there's a lot of reasons why. And the first two reasons are the two reasons that govern just about everything in our life: time and money. Trying to gather information from every item in the population or every member of the population is going to take a lot of time, and it's going to be expensive. So we use a smaller sample to save time and to save money. Third thing here is difficulty defining the population. Now this might seem kind of weird, like, well, we just defined the population above, but did we really? We said we only care about the voters who will vote in that election. Well, if you ask somebody, hey, are you going to vote in the next election? And they say no, and so we decide they're not in our population, so we don't include them in our sample, but then something happens over the next several days before the election happens, and it gets them excited, they decide they're going to vote. Well, now we had an incorrect population. We didn't include them even though they should have been in that population. Or the other way around, somebody that you ask, they're absolutely determined, yes, I am definitely going to vote. But then election day comes around and something happens at work, or maybe they get a flat tire on their car and they don't make it to vote. So we thought they were in the population, but they really weren't. So it can often be very difficult to define what your population really is, who is in it and who is not. Now this next one sounds like the same thing, but it's really quite different. This is changes over time. But I'm not talking about changes about who's in the population. I'm talking about changes to the members of the population themselves. Conditions. When we gather information from a group, we need to make sure we gather the information under the same conditions from every member of that group. If it takes too long, we risk those conditions changing. So we want to make sure that we can gather the information quickly. In an ideal world, we would gather the information from everybody in one instant, all at exactly the same time. Well, that would require you have one person gathering information per person that you're in the population or per person in the sample. That's not practical. So you still need to make sure that your group that you're gathering information from is small enough that you can get it done rather quickly. For example, back to our election example here, if we pick our sample and we decide we're going to gather the information over the course of 3 days, Monday, Tuesday, and Wednesday. And on Monday, we gather information from 1/3 of our population, but then that night in the news, story of a huge scandal for one of the candidates comes out. We cannot go ahead and continue to gather information from the rest of our sample after that because the conditions have changed. Many of the people we have already surveyed might have changed their mind based on that new information. They may have said they're going to vote for candidate A, but now that candidate A got caught embezzling money from their company, they've changed their mind. They're going to vote for a different candidate now. So we have to be able to gather the information quickly enough that the conditions are consistent. And this last one that I'm going to list here, now there are several others other than these 5. These are just the ones that are the most prominent, most common. But I could probably come up with 3 or 4 dozen reasons why you'd want to use a sample over a population. These are just the big ones. But this 5th one hopefully applies to a population that's not people, and that is destructive testing. Now, destructive testing actually applies to a larger group, a larger category of problems where the gathering of information changes the population itself. You know, when you go into a group of people and start asking questions, the questions you ask can actually start changing the opinions of the group that you're surveying. So you want to be careful not to do that, to subconsciously change the conditions of the group you're working with. But destructive testing specifically is talking about manufacturing. Let's say you have a part that you're manufacturing, and when you use it in use, it has to be able to hold a certain amount of force. So as we're producing those parts, we want to test them to make sure they're going to hold. But we're not just going to take the part and put the force that's going to be under in practice and see if it holds it. We want to do what's called an extreme test. We're going to test it until it breaks and see what force it takes to break it. And if that force that it takes to break it is sufficiently large compared to what it's going to have to experience in normal use, we say that part was definitely strong enough. Well, we can't test every part, because if we test every part, there'd be no parts to sell. The testing destroys the part. That's the destructive part of it. And so the reason we do it this way is, so if one part that we test takes 4 or 5 times the amount of force that it needs to before it breaks, we can be relatively sure that the other parts that are produced at that same time are probably strong enough to hold up as well. So we take a sample and we set that standard high enough that we know that if the parts in the sample hold up to that force, that the parts that are left over are going to hold up to that smaller force that they need to experience in their use. Now, like I said, there are a lot of other reasons to use samples over a population. Those are just some of the main ones. Now, when we take a sample, one of the things that we risk is something called sampling bias. And sampling bias is just a difference between the sample statistics and the population parameters. In a good sample, we want them to be the same. So there's something called a representative sample. That would be the case. In a representative sample, the statistics would equal the parameters. Now, unfortunately, we don't know what the parameters are. The whole point of taking a sample and gathering statistics is to predict what that sample might be, what those parameters, or sorry, not the sample, what those population parameters might be. If we knew the population parameters, there'd be no reason to take a sample. So we can never be sure that our sample is representative, because while we calculate the statistics, we don't know what the real population parameters are to compare them to. So all we can do is use good practices, what we call sound practices. Oh, wait. To increase the chances. Increase the statistical word that's often used is likelihood. Of a representative sample. And there are 2 main factors to consider here One is sample size. Now, the first part is pretty obvious. It has to be big enough. I can't just go out on the street and ask the next two people I see, what candidate do you plan to vote for in the next election? If the first one says candidate A and the second one says candidate B, I can't go back and say, hey, the population seems to be split 50-50. That would be too small of a sample. But on the other side, we have to be careful not to be too large. On the sample, little n is for the size of a sample. Big N is the size of a population. The size of the sample should be less than or equal to 10% or 0.1 times the size of the population. It has to be big enough. We always say at least 30, but in most cases for a population of voters like that, probably going to need to be way more than 30 to be representative. But it can't be too large, because if it's too large, we run that risk, that destructive testing thing we mentioned, how it could be, sampling could affect the whole population. We want to keep it small enough so that there is some sort of an influence from the experiment we do, that we're not altering a significantly large portion of the population by doing that. And then the second major factor that needs to be considered is random selection. And this is actually more complicated than you might think. So there's two types of random selection we're going to talk about here. A random sample. In a random sample, every item in the population or every member of the population has an equal chance of being in the sample. Now that sounds good, and it is, but it's not good enough. There's something more powerful called simple random sampling. And what simple random sampling is once we have determined a sample size, remember that sample size is just that small letter n. Once we've determined that, all possible samples of size n have equal chance. So let's look at some sampling techniques and discuss whether they're random or simple random samples. Now, the first one is called a convenience sample. And a convenience sample is simply you take the data that is easy to get. This could be ask your friends. You go out on the street and just talk to the next 50 people you see, whatever. This is not good. It is not random. Because people that you don't know or that don't happen to be on the street at that time you're out there have no chance of being in the sample. We have systematically excluded a large portion of the population from having any chance of being in that sample. Now, more common would be something called a cluster sample. Now, in a cluster sample, we divide the population into groups. But the groups are based on proximity. In other words, how close are they together? And ease of gathering information. The ease of gathering data. So what does this mean? Let's say I want to sample students in your high school. And what I want to do, rather than just picking individual students and then having to go track down those individual students and ask them the question that I need, what I'm going to do is I'm going to say I'm going to go during 5th period of the day, and all my students are in some class at that point of the day. I'm going to randomly select classrooms, and I'm going to go to those classrooms. I'm going to gather data from everybody in that classroom. So we randomly select clusters, and we gather information from each of those selected clusters. What it allows me to do is it allows me to conserve resources. Rather than having to go around the whole school and track down individual students, I can just go to a classroom and get 15 or 20 responses right there, all at once. Now, it is random. If done correctly, and if all the classes are approximately the same size, every student in the school has an equal chance of being selected. However, it is not a simple random sample. SRS is the abbreviation I will use for simple random sample, because it is not possible for two students that are in the same class at that time. It's not possible for one to be in the sample and one not to be in. So there are samples of size n that are not possible because of that. Next, we're going to look at a stratified sample. And in a stratified sample, we still divide the population into groups. This time, however, instead of dividing it into groups based on ease of gathering information, we divide it into groups based on likelihood of similar characteristics. So let's say we wanted to gather information from people that have an interest in the school. So let's say we want to gather information from students, but also from staff and from parents. So there's a logical division of groups. We'd have one group would be the students, one group would be the staff, one group would be the parents. So then we select a proportional amount from each of those groups. So let's say there are 6 times as many students as there is staff in the school. So we would randomly select 6 times as many people from the students as we would randomly select from the staff. Parents might be about the same number as students, so we would select about the same number of parents as we would students. This is random. Every person that's involved has an equal chance of being selected. But once again, it is not a simple random sample, because it's not possible to accidentally choose a sample that's all students or all parents. Now you might say, well, that's a bad thing. That would be a horrible sample if it was all parents. Yes, it would. But simple random sampling allows for the possibility of those bad samples. Our data analysis techniques take into account finding the probability of a significant appearance of data to be just due to a really bad sample. And so we have to leave that possibility in there. So a stratified sample, in most cases, if you're looking for an accurate description of the population, it is the one that probably gives you the highest chance of an accurate description. But statistically, it's not a usable sample because it doesn't allow for those really, really bad samples to be taken. Next is a systematic sample. And in a systematic sample, we randomly select a starting point. And then the system takes over from there. So the example here might be in manufacturing. Let's say we need to test 1 out of every 40 parts produced. So we're going to randomly select a number 1 to 40. And let's say that that ends up being 29. So then we're going to test the 29th part, and then every 40th part after that, the 69th part, the 109th, the 149th, 189th, 229th. The system takes over. This is random because every part has a 1 in 40 chance of being selected. But once again, it is not a simple random sample because it's not possible to select 2 parts in a row. The system doesn't allow for that. So all of these sampling techniques, other than the convenient sample first, that's pretty much always a horrible way to gather data. But these other 3, the cluster sample, the stratified sample, and the systematic sample, are all valid ways of gathering data in certain circumstances. But as far as doing a statistical analysis, they are not good sources of data for statistical analysis. So it comes down to, what is the simple random sample then? Well, a simple random sample is simply, if you're looking at people, you could write down their names on pieces of paper and throw them in a box. If you're looking at items, you could assign them a number or whatever. But you can, let's just say we're dealing with people, so we're going to put the names in a box, mix them up, and draw them out. Or draw out n items. This is, like the big tumbler you see at raffles and stuff where they throw them in there and draw them out. That is a simple random sample. There are no adjusting done to make sure that we don't exclude one group or another. The chances of getting a bad sample are still in there. And so we can account for those mathematically. So anyway, once we have the sample, we are then gathering the data from it. And in any point, any statistical study we're doing, we are asking a question. So in the example we've been using, the question is, who do you plan to vote for? We could ask, how many classes are you taking? Do you own a car? Yes or no? How many children are in your family? Those are all questions that could be asked. The random variable is the answer to that question. And so our random variable can take on a few different forms. It can be what we call categorical. Categorical random variable, sometimes called qualitative because it's measuring a quality. The answer to the question puts you in a category. If we ask you, what's your favorite color? That puts you in a category of people that like blue or red or pink or purple or green or black or whatever. If we ask, do you support this proposal? Yes or no. All yes or no questions are categorical. You're put in the category of being in favor or against. Who do you plan to vote for? That's categorical. You get put in the category of people that plan to vote for each candidate. Those are categorical questions. Then we have numerical random variables. So here again, the answer is a number. Now there's two important distinctions between two different types of numerical random variable. One is discrete. Discrete numerical random variables are items that can be counted. Like if I ask, how many cars do you own? How many siblings do you have? How many classes are you taking? Those are all things you would count. Continuous are things you would measure. How tall are you? How much do you weigh? If I give you this task to do, how long does it take you to complete that task? All of those are things that are measured. Now, there's obviously some gray areas in between here of, well, if I'm timing a task, can I count the seconds? Sure, but how did you decide that you wanted to just time it in seconds and not tenths of a second or hundredths of a second? Oftentimes, measured things, we have to artificially or just arbitrarily decide on rounding. We could time the time it takes to do that task to as small of a number as we want to, but it's not practical. We're going to, at some point, arbitrarily decide that we're only going to go down to the hundredth of a second, or whatever we decide to go to. Whereas with discrete, there's natural rounding. One that always causes some debate is money. Well, money has a natural rounding at the penny or the cent, 2 decimal places for dollars if you will. So even though that's less than 1, there's a natural rounding at the penny. So that could be considered discrete. Once you've determined that natural rounding, you can count the number of items that fit that rounding. So as we are going through these samples and different things, we want to make sure we get a good sample. We're going to talk about, once we gather this data, how we organize it starting on Friday. But we want to look at gathering good data. And I'm going to say reliable data. And we mentioned the term sampling bias before. We want to just talk about avoiding bias. To avoid bias, it's important to understand some of the types of bias that are out there. One is selection bias. So selection bias is one of the more common ones in sampling. It's where the process of choosing the sample excludes some of the population. The process of selecting the sample, that's where the selection bias comes in, excludes part of the population. So in other words, let's say that we are going to just use phone numbers, randomly select phone numbers to survey people for who they're going to vote for. Well, if somebody doesn't have a phone, you know, it's hard to believe that somebody wouldn't have a phone in today's day and age, but they exist. If somebody doesn't have a phone, we can't select them. Or if they share a phone, which one of the people do we gather information from? One of those people is going to be excluded. Measurement or response bias is another one. So this is a little bit different. The method of gathering information. Excludes part of the population. So maybe we got a list of the voter registration. So we had all the voters and we selected some of them. But then we decided that we were going to call them at 6 o'clock at night. Well, people that are working night shift or second shift might not be able to answer their phone at that time of night. they wouldn't be able to be measured. Even though they were selected for the sample, we couldn't get information from them, so their data wasn't included. That's part of the measurement or response bias that keeps them from being part of the sample. And then one that's always a problem, this is a huge one in any sort of statistics, it's non-response bias. And this basically comes down to can't force people to answer. For the U.S. Census, it is actually a federal crime to fail to respond to the U.S. Census. But there's still thousands of people every year that don't. How are they going to enforce it? We're not going to put 10,000 people in prison because they didn't fill out their census report. It just doesn't work. It's just not practical to get people to respond. I used to do a lot of statistical research in college. I worked with the Statistical Research Center at UW-Madison. When we sent out a mail-in survey, if we got a 30% response, that was huge. That was very rare. Most of the responses were closer to 15 to 18% on mailed out surveys. So you think about it, there's that other 80 to 85% out there that didn't respond. What are the chances that they have similar opinions? There's a lot of things that are done out there that might, just the way you package the survey or envelope, that might draw people with certain opinions to be more likely to respond than others. And there's actually big money spent every year on, we'll talk a lot about psychology when we talk about statistics, about quietly, subliminally invoking that psychology to get the response that we want. In a lot of cases, in the commercial world at least, statistical studies are being forced on a business by a government regulating agency. And so the business needs the results to come out a certain way, so they just design the survey so that they get the results that they need. One example is we did a study where we sent out political surveys, and we were able to acquire from the Wisconsin Republican Party and Wisconsin Democratic Party envelopes with their emblem on them. And we sent out 500 surveys in each type of envelope. Well, the surveys themselves were identical other than an emblem on the top of the paper indicating which envelope they went out to. No big surprise that the surveys that went out in the envelope for the Wisconsin Democratic Party came back with more liberal responses, and the surveys that went out in the envelope for Wisconsin Republican Party came back with more conservative responses. Because you think about it, if you're a conservative person and you get an envelope that says from the Wisconsin Democratic Party, chances are you don't even open it. You're probably going to throw it away. So there's little subtle things that can be done like that can change the responses. Okay, so that's all the vocabulary we have for today. Good news is there's no homework today. We will be starting the homework on this on Friday when we start looking at organizing our two types of data, the categorical and numerical data. For now, you guys have a great day, and hopefully we'll see you all on Friday.